let us start with first topic, that is transmission. First topic, that is transmission. Yeah. First topic, that is transmission. Okay. What is a transmission line? What is a transmission line? See, first of all, power is generated. I'll draw the single line diagram. Yeah. Power is generated at the generating station. See, every my word is a question, is a bit. Okay. Power is generated. Generally, we use synchronous generators. Generally, mostly 99% of the generators are synchronous generators. Only 1% are induction generators. DC generators are not used. Okay, DC generators may be used for the local users purpose, but they are not connected to the grid. One more topic I forgot is HVDC. Yeah, HVDC. HVDC, you see, in HVDC only outlines we will see. HVDC itself is a subject, in fact. Okay, we are going to see till what extent we require for this BEL examination. We are not going to get in deep into the HVDC. Yes, don't think in wrong way. Why we are not discussing in depth? Not required, basically. Okay, HVDC about converting stations and their design and all, not required for your BEL examination. What type of converter, efficiencies, so like that, whatever that is important for our exam. Okay, without missing even 0.0001% also we will discuss. Okay, make sure that you are connected with the class. Okay, make sure that you are connected with the class. I hope it is audible to all of you. Lasya, Pawan Kumar and all of you, I hope it is visible, audible and visible also, right? Power is generated. So generating stations are located far away from our load centers. See, load center, again a new word. Load center means the factories or the, I can say, industries which consume electrical energy are called as load centers. Okay, synchronous generator. But that power to be transmitted, in layman's language, that power should be transported. See, I am wearing this t-shirt. It is manufactured somewhere and it got transported from there to here to Hyderabad. In Hyderabad I purchased, for example, I am saying. Power also generated at remote places. Why? Because generating stations require a lot of area. Generating stations require a lot of area. Okay, so that much area is not possible in the cities. Okay, and it requires a lot of resources like water. A lot of water is required. In suppose Hyderabad is a big city, at the middle of the Hyderabad it is not possible to establish a thermal power plant or nuclear power plant or hydro is impossible. Why? Because hydro is kept at where water is there at with high potential energy, means at hilly stations. So generally this is also one of the question. The best suitable place for the placement of or for the placement of hydroelectric power plant is at hilly areas. So because that is at the height. Okay, natural I can say height is created at the hill stations. Okay, now for thermal power plant, lot of pollution. Okay, nuclear power plant, it is danger to be there in the, I can say, rural areas, right? Rural or urban, whatever it is. Suppose urban area, suppose if you take Hyderabad, sorry, I used wrong word, rural. Rural areas also, yes, we are not going. We are going to place it in remote places. Any power plant, not in rural areas. So means somewhat near to rural area, but never it is going to be in urban. Okay, urban means cities, right? Sir, wind power plant, where there is a possibility of getting wind, there only wind power plant can be established, right? Generally places like Rajasthan or hilly areas like Tirupati, there is one place, Tirupati. So at where wind speed is high, wind speed is supporting for the establishment of power plant, right? But solar power plant can be established. Means if you have good land, and solar power plant can be established anywhere, no problem. Means where there is a places like I can say places like Kashmir, where see during winter season people are unable to see the sun. So at those places, in the summer season there it is very hot. We will get solar power, but in winter season somewhat it is difficult. But in places like Rajasthan or Andhra Pradesh or Telangana, in these places, yes, happily we can put I can say solar power plant. Okay, so see, power is generated remotely at some place. It has to be transported, transmitted. Transportation is layman's language, transmission is our technical language. Now, but we are not going to transmit as it is. We are going to step up the voltage, Generation will be done at lower voltage comparatively to the transmission voltage. Don't think that lower voltage means are 1 volt or 2 volt. Compared to transmission voltage levels, generation voltage levels are very less. Now we are discussing one very important thing. Why we are going for higher generation voltage levels? That is, see, for a constant power, see, power is constant. Okay, power cannot be increased. Okay, power cannot be decreased or increased. Just like energy neither be created nor be destroyed. It will be converted from one form to another form. In the same way, power also, law of conservation of power also valids good, as I'm saying, like law of conservation of energy. Okay, for constant amount of power means I am talking about apparent power. We have, see, you studied about network analysis. In network analysis you learned about active power, reactive power, and apparent power. Apparent power means apparent power S is the combination of real power and reactive power, but there is a phase angle difference of 90 degrees. That 90 is represented with Z. Okay, now I want its magnitude of S is equal to root of P square plus Q square. If I draw a power triangle, which is a right angle triangle, this is P and this is Q, this is S. Let me take this angle as theta. Let me take that. You can take it as phi also, but phi and Q, there is somewhat confusion. That's why I taken theta. Right? Now power factor, or we'll talk about power factor later. Now tell me, so from this one, if I write cos theta, which is called as power factor, that is equal to P by S. P by S. All these are magnitudes, please. Once you are, this is a length, na? Length means magnitude only. Don't length means magnitude only, right? Mod P by mod S, right? Now from this one, P is equal to S cos phi. Yeah, you have to remember S cos theta, sorry, S cos theta. This is in megawatt. Now if I write sin phi is equal to opposite side is Q divided by S. Now from that, Q is equal to S sin phi. Now if I write a tan phi, Q is inverse. Yeah, this is reactive power. Q is reactive power. If I write a tan phi, yes, just a minute, let me erase here and write somewhere here. If I write tan phi, what is tan phi? Tan phi is equal to Q by P. Yes, so from this one I get Q is equal to, yes, Q by P. Yeah, opposite side by side. Q is equal to P tan phi. Q is equal to what? P tan phi, right? So there are the useful formulas. Means, so there are a lot of formulas for P, Q, and S. These are one set of formulas. Suppose if you have the data of phi and P, you can find S, you can find Q, right? Yeah. Now observe carefully here. We all know that S is the apparent power. S is called as apparent power. Okay, we are electrical engineers, therefore we must know what is apparent power and all. Apparent power, whose units are MVA in a power system, but because our power is very high, M stands for mega, power is very high. Okay, kVA, VA, that formula is V into I conjugate. Yeah, V into I conjugate, not just V into I. Okay, sir, this is for single phase. What about for three phase? This is for single phase system. For three phase, yes, three phase is equal to root 3 VL into IL. If you want magnitude, root 3 is root 3 VL into IL, right? MVA, root 3 VL into IL, right? S is equal to root 3 VL IL, right? Sir, from this one, suppose if S is there with you, where VL is what? VL is nothing but line voltage. VL is line voltage, that is equal to root 3 times of phase voltage. That is equal to root 3 times of phase voltage. IL is equal to I phase. You may be thinking, sir, VL is equal to V phase, IL is equal to VL is equal to root 3 times of V phase, IL is equal to I phase is valid for star connection. Means our transmission line is connected in star or no. Transmission line relation matches with star. Transmission line is not a machine. Okay, to have star delta connections. Transmission line is not a machine. Only machine winding will have star or delta. Transmission line is not a machine. But transmission line voltage current characteristics matches with star. Transmission line voltage current characteristics matches with the star connection of a machine, right? Now S three phase is equal to root 3 VL into IL. Sir, I want a current magnitude. Yes, three phase value divided by simply root 3 times of V phase. This will be definitely in kiloampere. So because this is in MVA, voltage, yeah, kV. Our voltage, see, minimum voltage level mostly in generation is I can say 3.3 kV, 3.3, 6.6, 11 kV, up to 33 kV is the generation. In advanced countries like Germany, they have generator which can withstand 33 kV, means which can produce 33 kV, not withstand, which can produce 33 kV. Okay, sir, why we can go for more voltage also? Na? What is the formula for induced EMF? E is equal to from electrical machines. From electrical machines, induced EMF, either it is true for a transformer, it is true for synchronous machine, it is true for induction machine also. In fact, it is true for DC machine also, but instead of frequency, we have to put something. That's why I'm not getting into machines. Okay, for all AC machines, E is equal to what? 4.44 phi F and a number of turns. Number of turns, let me keep it as T, phi FT. Phi FT, right? Now, if you see, I want to increase induced EMF, then I can go for more number of turns, right? Say flux beyond certain limit, it cannot be increased due to saturation. Frequency is fixed in India. Yeah, all our generators are connected to grid. Frequency is fixed to 50 hertz. It is not possible to have more than 50 hertz frequency. Now, the only possibility is I can go for increment in number of turns. If you go for more number of turns, size of the machine will increase. That is first disadvantage to go for high voltage, high induced EMF. The second disadvantage is if more is the voltage, more insulation. Suppose, see, if this is a machine, if you take, means for just only a rough way I'm doing, this is phase A here, this is phase B here, phase C here, 120 degrees. It means all this belongs to phase A, this belongs to phase B, this belongs to phase C, and like that. But here between this conductor to this conductor, between these two conductors, I have to keep insulation. I have to keep insulation between these two conductors. I have to keep insulation. As we are going for a higher and higher voltages, as I am going for higher and higher voltages, more insulation is required. Therefore, size of the machine will increase. Size of the machine will increase. So that's why generally our generation voltage levels are, yes, generation voltage levels are, a question can be given, what are the generation voltage levels? Generation, yes, generation voltage levels are, voltage levels are, the question can be given which of the following is not generation voltage. Okay, generally it will be multiples of 1.11, okay, or 3.3 kV, comma 6.6 kV, comma 11 kV, comma sometimes 3.5 kV also, sometimes, comma I can say 33 kV, but never 66, 132 or generation voltage levels. It's quite less when compared to transmission voltage level, right? Now in generation voltage level is okay, we understood. Now for a constant power, S is equal to root 3 VL IL. Sir, why you are writing always S is equal to root 3 VL IL? Why not S is equal to V into I? Our power system is always three phase, never it is single phase. Sir, if at all there is a single phase transmission line in distribution, that fellow will clearly mention as single phase transmission line. Do remember one thing? If the number of phases are not mentioned, do remember one thing? If number of phases are not mentioned, by default, the given transmission line is a three-phase transmission line. By default. Right? By default, the given transmission line is a three-phase transmission line. Suppose if I say a 220 kV, a 220 kV transmission line. 220 kV transmission line means that is a three-phase transmission line. Suppose even if I say 11 kV transmission line, that is a three-phase transmission line. If it is a single phase transmission line, that examiner or the author will mention it as a single phase 11 kV transmission line. That fellow will mention, otherwise always it is three phase. Okay. Now tell me, for a constant power, this is fixed, for a constant power, if I am going for more voltage, obviously my current will decrease. Current will decrease. Yes. If I'm going for more voltage, current will decrease. Yes or not? What is the power loss in the transmission line formula? Yeah, transmission line is made up of conductor. Yeah, transmission line is made up of conductor. Every conductor will have some resistance. The power loss due to resistance is, power loss is equal to I square R, 3I square R in fact. 3 square R. Sir, why 3 square R? Three phase. Yeah, three phase power loss. I told you, by default we are discussing about three phase. Now tell me, if as voltage as for constant, this is for fixed amount of power. Power is fixed, okay, constant amount of power. I am sending that fixed amount of power. If I go for more voltage, current will decrease. If current is decreasing, I square further will decrease. Suppose if if voltage is doubled, then I will get halved, but power loss will be reduced by 4 times, right? Power loss reduces. So we are going for higher and higher voltage of transmission to reduce the transmission power loss. That is the first reason. That is the first reason, right? Now let me give you a question here. Let me give you a question that is for fixed amount of for fixed amount of power transfer, the power loss the power loss is directly proportional to directly proportional to option A, B, V square, C 1 by V, D 1 by V square. Please do this. 1 minute is the time I am giving it to you. Please try it. Otherwise, I'll take it up. Answer, please.
V, sir.
Inversely proportional to square of voltage.
Very good. Option is D, D for Delhi. Yeah, I'll do this. Someone told C. It's not C, man. It's not C. It's not C. Okay. Pawan Kumar given answer as not C. Given yes, A. Option is C. C for Chennai. Okay. Sorry. D. D for Delhi. Let me do the answer. Okay. So simply power loss formula 3I square R. I don't want to waste our valuable time in simple things. Okay. What is S? S is equal to root 3 VL IL. See, you must get habituated for this. Sir, here IL you are writing, here I you are writing, IL and I both are same. Why? Because for transmission line, IL and I phase and I all three are same. Voltage is root 3 times of phase voltage. Line voltage is root 3 times of phase voltage. But current is line current, phase current, both are equal always. Right? Now. Right. Now, but see, in the given options, nowhere I is there. Therefore, anyhow, the resistance, once transmission line is designed, resistance is fixed. Okay, 3 is fixed. Now, power loss is directly proportional to I square. Okay, let's go to the next page. Power loss is directly proportional to I square, but I is not there. Okay, S is equal to root 3 VI VL IL. From this one, I get IL as IL is equal to S by root 3 VL. Put there in place of I, power loss is directly proportional to S by root 3 VL whole square. But that fellow very happily told it is a fixed value, constant value. I'm crossing y because it's a constant. Whenever we are writing directly proportional, the constant should be removed. Root 3 square will be 3. Remove it. Then power loss is directly proportional to 1 by VL square or V square, whatever it is. Right? Yes or not? And one more thing I forgot to write. S is equal to root 3 VL, that is equal to 3 times of V phase into I phase. 3 times of V phase into I phase. Okay? Because so you may be thinking, sir, how you wrote this? Yes, I'll write this. What is VL? This is root 3. VL is root 3 times of V phase. IL is what? I phase. So from this one we get 3 times of V phase into I phase. 3 times of V phase into I phase. Right? That is also one of the formula. Now one more thing. P is equal to S cos phi, right? P is equal to S cos phi, where cos phi is what? Power factor. S is what? S is equal to, yes, mod V into mod I into 3 times if you take phase values, right? Okay, we'll discuss about that formula later. This whenever the time comes. Means I want to tell you about power factor. If power factor is low, what happens? So those things just I thought of discussing, but we'll discuss. Okay, later we'll discuss later. Right now, come to next stage. See. I'm giving the next question, try to answer. As I told you, I'll go with the more number of questions, as many as possible, right? For fixed length of transmission line, comma, same material means transmission line is made up of, suppose, aluminum conductor with steel reinforced. In first case and second case, both the cases same material, I mean to say, comma, same power transfer, comma, for same power transfer, if for same power transfer, if voltage, if transmission voltage, not just voltage, if transmission voltage is increased by n times, then power loss is dash. You know, I taken a lot of time for writing the question. For answering it will take 1/4 of that time. Okay, within that very small amount of time you can solve. Answer is decreases by n times. Option B, decreases by n square times. Sorry, let me add a page here. Yeah, option C is increases by n times. Option D is increases by n square times. This one we already did, but another way, just a framed question in another way. We did that one already.
Decreases by n square times.
Yes, good. Decreases by n square times. Yes, that is very, very simple, man. That is very, very simple. I'll do this. Same, S is equal to S1 in the first case, V1, I1. Let's take single phase, no problem. See, this is only for comparison purpose. Nah? Whether root 3 V means 3 is there or not there, it is why, because I'm taking directly proportionality, it is not going to much affect our analysis. Now, S2 is equal to V2I2. S2 is equal to V2I2. But same amount of power means S1 is equal to S2. V1 I1 is equal to V2 I2. But one thing is very sure, that voltage is increased by n times compared to previously. Means V2 is n times of V1. and I2 is obviously I2, V1 gone. So I2 is equal to simply I1 by n times we got. I2 is equal to what? I1 by n times. Right? I2 is equal to I1 by n times. Now, what is power loss? Power loss is equal to, power loss in the first case is I1 square R1. I1 square R1. Now, what is the power loss in second case? Power loss in the second case is I2 square R2. But what is R1, man? What is R1? See, power loss 1 is equal to I1 square into rho 1 L1 by A1. Yeah, resistance rho L by A. Right? Power loss 2 is what? Power loss 2 is equal to I2 square into rho 2 L2 by A2. Power loss 1 is I1 square into rho 1 L1 by A1. Let's divide these two. Let's divide these two. Whatever that is going to get cancelled, we cancel it first of all. Rho 1, rho 2, L2 will get cancelled. Now we are left with power loss 2 by power loss 1 is equal to what you get? I2 square A1 by I1 square into A2. Yes or not? Come on, man. Here two cases will exist. Here two cases will exist. That fellow did not discuss anything about the area of cross section of the conductor. Yes. Did he said that area is fixed or not fixed? Suppose transmission line is already designed, then it is not possible for us to change the area. Na? See, you already designed a transmission line whose length, area, material, everything is fixed. You can change voltage, you can change power, you can change current, but not area of cross section. If area of cross section is already fixed once designed, means after design is my heading. After design, yes, design is already done. Then tell me A1, A2 gone. Now power loss. What is I2? I2 is I1 by n times whole square by I1 square. I1 square, I1 square gone. You are left with 1 by n square. This is after design. This is after design. Right? Means power loss 2 is equal to 1 by n square times of power loss 1. So this is what after design means, after transmission line design. We designed it already. Means it's not possible for us to change area of cross section. Suppose only for the sake of theory, or then we can think like this. Current is decreased, I2 is equal to I1 by n times. Then obviously area of cross section I will take A1 by n times. Right? Then obviously area of cross section I will take A1 by n times. Why do take total area, man? Why do take total area? It is useless. Now cost is going to save for me. Cost is going to save for me, right? Yes or not? Yes, this cost will be saved. Therefore, now you tell me power loss 2 by power loss 1 is equal to what we got here. That is I2 square A1. Yeah. I2 square A1 by I1 square A2, that is equal to I2 is I1 square A1 by n square into I1 square A2. But one this I1 square let can cancel. A1 by n square into A2. But A2 is what? A1 by n times. Right? So A1 gone, this gone, 1 by n times means simply I can write power loss 2 is 1 by n times of power loss 1. Right? I hope you got it. Lasya, Pawan Kumar and others. Yes, acknowledge, man. I'm asking you guys, right? Can I give next question, please? Yes, that is before design. That is before design. Okay. Yes or not? Come on, man. Yes are there or not there? Yes, you're there, but you're not replying. I don't know why. Let me give the next question. For fixed amount of power transfer, S, I'm not writing power transfer and all, waste of time. S means power, comma, same length, comma, material is same, means rho is same, material, comma, if for same power loss, yeah, I want same power loss, yeah, power loss should be same, power loss, the area of cross section of the conductor, area of cross section of the conductor is dash. Option A, decreases by n square times. Option B, decreases by n times. Option C, increases by n square times. Option D, increases by n times. Try to do it, please, all of you. Do it. I'm waiting for your answer. Once you are done, then I'll take it up. Raman, answer. At least you can answer, sir. We don't know or we are not getting.
Decreases by n times.
We'll see. See, it's not just we have some method. Na? S1 is equal to S2, madam. V1 I1 is equal to V2 I2. V1 I1 is equal to V2 is n times of V1. Right? Did I mention voltage increases by n times? Yeah. The obvious case is voltage increases by n times. I forgot to mention here. For fixed amount of power transfer, same material, same length, same material, if same power loss, the area of cross section of the conductor required is dash if voltage increases by n times. Yeah, we are actually in the discussion of voltage increases by n times. Okay, sorry, I forgot to mention that, in fact. So V1 I1, so here also I2 is equal to I1 by n times, then obviously area of cross section is equal to A1 by n times. But what he want, no, sorry, he's asking about the area itself, but he wants same power loss also. What is power loss? He wants power loss 1 to be equal to power loss 2. What is that? 3 I1 square R1 rho 1 L1 by A1 is equal to 3 I2 square R2, nothing but rho 2 L2 by A2, right? Yes or not? Come on, man. So row 1, L1, row 2, L2 gone, 3 gone. So I1 square, keep it as it is, I1 square by A1 is equal to, I2 is nothing but what? I1 by N whole square, 1 by A2, 1 by A2. So 1 by A2, let's keep it this way. Yeah, question itself is about the area of cross section, madam. Right? So I1 square gone. So 1 by A1 is equal to 1 by N square into A2. So from this you get N square A2 is equal to A1. So from this one A2 is equal to what? A1 by N square. A2 is equal to what? A1 by N square. Right? So answer is decreases by N square times. Decreases by n square times. Option A is perfectly suitable for this question. Option A is perfectly suitable, right? Next, see, transmission line is a power carrier from one place to another place. So somewhere we started there, single line diagram, we left unfinished there. There will be a transformer. Yes, purpose of transformer is to increase the voltage, step up the voltage. We should not use the word increase or decrease, step up the voltage. Okay, generation, step up transformer. After that, the transmission line, then step down the voltage, step down transformer, then load. But generally on the transmission line no one is going to put the load. Okay, that would go to distribution and all, that is not required for us as of now here. Okay, now what is this? This is transmission line. This is step down transformer. This is, yes, step up transformer, and this is the load. This is generator, right? Now see, transmission line is carrying power, that's all, from one place to another place. But transmission line alone cannot do that job. It requires some support mechanically. What is that called? As transmission tower. About tower and all those things I'll discuss here. All those things I'll discuss. Okay, come here. Purpose of tower: you take one wire. If the wire length is exceeding some value, then wire may oscillate like anything to and fro. That's why if we connect that wire to some fixed, I can say, points, rigid points, then it won't oscillate. It will not create any problem, right? The purpose of transmission tower is to provide mechanical strength for the transmission line. Okay, now this is the transmission tower I'm drawing. This is the transmission tower. I hope this area is visible to all of you. Transmission tower. This is transmission tower, which is kept on ground. This is 0 volt. This is transmission tower. Transmission tower. And this tower is made up of what? Yeah, question may be asked, with what material transmission tower is made up of. If you make the transmission tower with iron, after a few days it will disappear. Why? Because iron is subjected to corrosion. You know what is corrosion, right? Corrosion or rusting, right? That's why we have to make it with steel, that to galvanized steel, and it is made up of the material. Yeah, it is made up of the material galvanized steel. It is the material. This is made up of galvanized steel, right? And there is one more tower here. Let me draw one more tower here. See, this is one more tower. See, I am giving you all the concepts. You know, these indicates that our transmission tower is kept on the ground and the voltage of the tower is 0. At any point on the tower, the voltage is 0. Yeah, at any point on the tower. I'm talking about the tower, not the line. If line is 0 volt, then no power, nothing, right? Now, so this is also two towers. Now can I connect directly my transmission line to this tower? No. If at all, if you connect, which fault will happen? Line to ground fault will happen. You are taking one of the phase A or phase B or phase C. Suppose you are connecting that one to transmission tower, which is at 0 volts, but your line is at some 11 kV. If you take the phase voltage 11 by root 3, or if it is 220 kV, the phase voltage is 220 by root 3. Right? If you connect to this tower is connected to ground. See, 220 kV connected to ground, dead short circuit fault, LG fault, line to ground fault. Therefore, we have to put insulation, that is called as overhead line insulation. We have a separate discussion related to overhead line insulation. Okay, types of overhead line insulators, types of over voltages, lightning over voltages, okay, switching over voltages, which one is high, okay, for what voltage, which voltage is, a lot of things. Okay, if you are willing to listen, lot of things we'll discuss. Okay, this is called as cross arm. Yes, cross arm. Yeah, the name itself, you see, this is looking like a arm, but it is cross. That's why it is called as cross arm. Why I am telling even that also, so that you will remember the terminology easily. That's all. This is cross arm. Here also there will be a cross arm. Here also there will be a cross arm. Okay, now can I connect? Now cross arm is also metal, which is at 0 volt. Yeah, this is 0 volt. Therefore, what I do is I am going to put some insulators here. Insulators are made up of porcelain. These are called as overhead line insulators. Those are what? Overhead line insulators, right? Now, these are also overhead line insulators. Overhead line insulators. Now, I am connecting my transmission line here. Now there is no problem. Now there is no problem. Why? So this overhead line insulation resistance will be in terms of mega ohms. This is 0 volt, this is mega ohms. Small amount of current will be flowing through this. That is called as leakage current. That is called as what? Leakage current. And that leakage current will be in terms of milliamperes or microamperes. Why? Because insulation resistance is very high. That leakage current will flow to ground. What is leakage which we don't want? Sir, if we don't want that leakage, why we are not stopping? If you want to stop that current, how much resistance should be there here? Infinity. Can you give me any insulator which can provide infinite amount of resistance? Not possible, right? A small amount of, negligible amount of current is flowing. You know, one time one question was asked, the reason shunt conductance of the transmission line is neglected is, the reason is the leakage current. This is conductance only, na? It is conducting. Actually, it is insulation resistance. It should not conduct. Resistance means it is going to have some finite resistance, then definitely finite conductance. More is the resistance, less will be the conductance, less will be the current. As the resistance, insulation resistance is very high, conductance is very low. Resistance is very high, conductance is very low. Leakage current is very small. Leakage current is very small. Therefore, we neglect the shunt conductance, right? And this is your transmission line. This is your transmission line. It's okay, sir, we understood. Are there any other auxiliary things to discuss here? Yes. Now, tell me, lightning will occur in the form of current. Lightning always attacks the topmost conducting body on the earth, right? Which is the topmost conducting body? Obviously, transmission line. You may think that transmission tower is more height compared to this one. Now, at the tower, near to tower, if it is occurring, the lightning will strike onto the tower, then it will go to ground. But between tower to tower, there is a distance. Now, suppose if lightning stroke, I'll take with the black color. If the lightning stroke occurs somewhere in the middle, let me take in the middle. If the lightning stroke occurs somewhere in the middle, this is a lightning stroke. Yes, this is lightning stroke. Somewhere occurs in the middle, then that lightning will enter like this. Insulation will damage, or it will enter into the next transmission line, into the equipment, into the transformer. If lightning enters into the transformer, almost its magnitude will get double, blast will happen, right? Therefore, what we have to do to avoid this lightning stroke onto the transmission line, actually topmost conducting bodies once upon a time was trees, but our transmission towers are too high compared to trees. That's why most subjected things on the earth for lightning strokes are transmission lines. To protect the transmission lines, we are running a wire throughout the transmission on the top of the transmission tower. This is called as guard wire, okay, guard wire or shield wire or earth wire, these many names it is having. If at all lightning stroke is occurring, it will enter onto the guard wire. Yeah, from guard wire happily it will travel, some part it will travel, it will go to ground, no problem. Lightning is going to ground, no problem. Lightning should not enter into our system. Our system is transmission line, transformer, distribution line, transformers, and our electrical equipment, CT, PT, whatever it is. And some part will travel like this and it will go to ground. You may think, sir, it is coming this way. Why it is not going this way? Lot of resistance. Huge value of resistance instead of lot of resistance. Huge value of resistance. We all know that almost earth resistance is zero. Current always chooses short resistance path, low resistance path. Current always chooses low resistance path, right? So that's why no lightning stroke will go this way. Total lightning will go to ground. Total lightning will go to ground. Here also, total lightning will go to ground. Total lightning will go to ground, right? So this way, this wire name I want to write, this wire is called as shield wire. Yes, what is this? Shield wire or earth wire, or it is also called as ground wire. Shield wire, earth wire, or ground wire, right? Yes, so in that anything may be asked in the form of question. Right? So that's a small pause I given so that you look into it and you will understand the total story. Right? Right. Okay. Now, sir, with what material transmission line is made up of? Conductor, obviously, but there are several good conductors. In that we are taking aluminum. Okay. Transmission line is made up of aluminum. Okay. Sir, why not copper? Copper is not economical. Okay, somewhat costly compared to aluminum, right? And there is another reason also, that is electric field intensity. All at the time of corona we can discuss that. Okay, now transmission itself is a very big topic. Okay, don't think in one or two classes it is going to be finished. At least it will take 3 to 4 classes, complete classes, to finish transmission. Not 3 4, it will take at least 5 classes for transmission to complete, but I'll try to complete as early as possible by covering all the things. Okay, it's our main motto is to cover all the things required for your examination, right? Now, see, types of conductors. We have 3 types of conductors. We have a lot of types of conductors, but in power system, types of conductors. First one is solid conductor. We never use solid conductor. I will tell you, most of the people will say, sir, skin effect is the reason. No. The main reason is transportation. Suppose If you manufacture a conductor very stiffly like this, very stiffly, 1 kilometer conductor, how to transport it? So through helicopters? No. That's why we will manufacture small size conductors. Then we are going to, that a small size conductor is called a strand. Such several conductors we take and we twist together. Such several conductors we take and we twist together. That is called as a stranded conductor. That is called as what? Stranded conductor. Right? Yes or not? Yes. So main, see here, advantages and disadvantages, all three I'll write, you will understand. I do not have to put the heading advantage, disadvantage, childhood way of learning. Okay. The first point is transportation is not possible. It's a disadvantage. Transportation is not possible. First point. Second point is skin effect is high. This is also correct, but it is a secondary consideration for me. Skin effect is high. What is skin effect? We'll see later. Skin effect is high. If skin effect is high, what happens? Resistance increases. If resistance increases, voltage drop, power loss, everything will increase. Right? Third thing is good mechanical strength. Now tell me, third point is an advantage or disadvantage? Good mechanical strength. Tell me, good mechanical strength. Third point, this is an advantage. This is an advantage. These are disadvantages. Yeah, these are disadvantages. Those two are disadvantages. The last one is advantage. So what is the need of good mechanical strength? If mechanically it is good, it will be having more tensile strength. Whenever any wind comes, then it is mechanically strong. Okay. Now, something I want to tell you about sag. That is, what is a sag? Sag is denoted with S. Suppose these are two towers. Now onwards, for simplicity purpose, I'll draw a tower as a single line, and I'm most of the times I'll omit drawing those insulation resistances. Those will be there obviously. Don't think that insulation resistance are not there. How come sir will connect without insulation resistances that conductor to the towers? No, those are there, but I'm not going to show here. Right? I cannot stiffly connect my conductor this way. If I connect, what happens in winter season? Further it contracts, then it will break. Further it is going to contract, it will break. That's why what I do is I am going to connect it loosely, not this much loose. If this much loose, what happens? In the form of swing, it keep on swinging for front back, front back, front back. It is keep on swinging, so it will touch with someone or some equipment, some vehicle. Then short circuit is going to happen. That's why what happens is I'll connect this way. Let me draw once again. I'll connect this way. Okay, so this is your transmission line. This is your transmission line, right? Somebody is trying to enter the classroom now. I don't know, at the end. This is transmission line. See, this is the height of the tower. Yeah, this is the height of the tower H. Okay, now this is called as ground clearance. Okay, this is called as ground clearance G. G is ground clearance, H is the height of the tower. Now the distance from the lowest point on the conductor straight onto the mean length of the distance between two towers is called as sag. Sag should not be very high. If it is very high, ground means if the sag is very high, conductor will be like this, ground clearance will be very low. Ground clearance will be very low. If the sag is too low like this, during winter the conductor will contract. There is a possibility of the breakage of the conductor, due to which open circuit fault will take place. What happens due to that? Open circuit fault will takes place. Right? So all of a sudden, from types of conductors, from solid conductor to why you jumped into sag? I have some purpose. Sag is directly proportional to length between two towers and inversely proportional to tensile strength or mechanical strength. See, what is L? L is called as span length. Span length is the length between two consecutive towers. This is a span length L. This is called as span length. It is the distance between two consecutive towers. This is height of the tower. height of the tower, and this is called as, yes, ground clearance. This is called as ground clearance, right? Now, sag is directly proportional to L square by T. Now, more is the mechanical strength, less will be the sag. But okay, yeah, I have to discuss about strand conductor. Then I'll use but what happening. Okay, now for a solid conductor, good mechanical strength, less sag, no problem. Less sag, no problem. But now next conductor is stranded conductor. Yeah, why we are going for stranded conductor? Transportation is the main problem with solid. What is a stranded conductor? We are going to take like this. Instead of taking one big solid conductor like this, take small width conductors. I'll show here. Instead of taking this way, you take and you twist. This way you take and twist. This will become a stranded conductor. Okay. Now take always a central strand is one central layer is one strand. Central layer, not strand. Central layer is one strand. Okay. On that I'm going to take 6 more strands like this. Second layer with a different color. 1, 2, 3, 4, 5, 6. Let me write here. This is one first layer, second layer 1, 2, 3, 4, 5, 6. Third layer 6 will be the increment from one layer to another layer. Number of strands increment is 6 except from first to second layer. First to second only 5. After that, see, I'll write here. Third layer also let me put. Then I go for that. 1, 2, 3. Sorry. 3, 4, 5, 6, 7, 8, 9, just a minute, 9, 10, 11, 12, right? So these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so if I write this one in the form of series, 1 plus 6 plus 12 plus 18 plus and so on, means from second layer onwards the increment from one layer to another layer is by 6. Sir, how many I have to take? If you want big conductor, more means big size cross section area, more layers you take. You want less cross section area, you may take 2 layers or 3 layers, right? This is a series, right? Now with this first advantage is transportation is possible. Transportation is possible. Second one is transportation is possible. Second one is I can say skin effect is reduced. That is also advantage. Yeah, skin effect is reduced, but there is a disadvantage, that is mechanical strength. Mechanical strength decreases. I'll mark here, these two are advantages, but this fellow is a disadvantage. This fellow is a disadvantage. Then what to do, sir? Sir, actually previously what are the disadvantages are there? Sir, what happens if mechanical strength is low? If mechanical strength is low, sag is directly proportional to L square by T. If mechanical strength is low, obviously tensile strength is low, then sag will increase. If sag increases, then ground clearance decreases. Sir, what happens if ground clearance decreases? Safety will decrease. Safety decreases, you see. Ground clearance is decreasing, conductor is like this, sag is increased, ground clearance is decreased, Z2. So if someone or some equipment is or some vehicle is coming, then obviously there is a possibility of short circuit with that vehicle. Yes or not? Yes, right? Then what to do, sir? First of all, here I have a question, try to solve. In a 3-layer stranded conductor, the number of strands are dash. Option A, 3-layer. Okay, 3-layer. You can count, but there is a formula for that. If I give 10 layer, you keep on counting 1 plus 6 plus 12. So answer is 18, 19, 20. D is 7. Tell me answer. This is easy, but after this I will give you one formula for any layer how to find. After this I'll give you one formula for any layer how to find. I'm waiting for your answer, man. Otherwise I can proceed. Arey yaar, why you are not answering even this small question, man? One person answered. Answer is 19. Arey yaar, 3 layer na? 3 layer. Solution 3 layer is 1 plus 6 plus 12. You have to stop here. 3 layers. First layer, second layer, third layer. How much it is? 19. Option is B. We have a standard dedicated formula. Total number of strands I can derive if you want, but I'm not deriving as of now. If you ask, if you request me now, sir, please do the derivation. I do that. Okay. Total number of strands in an n layer stranded conductor is equal to, so derive karna, I have to derive it. Why? Because it seems I forgot the formula. See, I never remember the formulas which I can derive. Why? Because I am not going to write the examination, right? N by 2 into 2a plus sorry, just a minute, I do that. N by 2, n minus 1 by 2 into 2a plus n minus 1 minus 1, n minus 1 by 2a plus n minus 1 into d is 6. Okay, n minus 1 by 2 into, yes, 2 plus 6n minus 12, or anywhere I committed mistake. N by 2 into 2a. A is 6, sorry, this is 6, this is 12. Okay, 12 gone. This is 3. Yeah, 3n into n minus 1. If you want 3n square minus 3n plus 1, you have to add plus 1. Okay, this is the formula, 3n square minus 3n plus 1. Okay, sir, how you did it? I'll tell you. Array are 1 plus 6 plus 12 plus 18 plus and so on. From here it is forming like arithmetic progression. From second layer onwards it is arithmetic progression, not from the first layer. Why? Because arithmetic progression means the common difference should be equal, but here to here common difference is 5. The difference is 5. Next is 6. Therefore from 6 onwards it is falling into arithmetic progression, right? What is sum of n terms formula in arithmetic progression? Yes, sum of n terms in an arithmetic progression is n by 2 into 2a plus n minus 1 into d. But here I am taking from second layer onwards, therefore it is s n minus 1. Means in n layers, one layer is 1 that we kept aside. This will be, this is n minus 1. Now this is n minus 1 now, sorry. This is n minus 1. This a is the first term. How much is first term? First term is 6. Okay, then n minus 1 minus 1. This is difference is how much? Common difference is how much? In the AP what we take, and common difference is 6. Now total if you want, Sn if you want, you have to add 1, that first strand. The same 3n square minus 3n plus 1. 3n square minus 3n plus 1. Right? Yeah. See, for today I'll stop here. Okay, for today I'll stop here. Tomorrow I'll resume from there where we stopped. Okay, so better listen to the class carefully, practice the things, then every question you'll be able to solve, right? Any questions?